sigma squared. So u divided by sigma, it's a normal 0, 1. It's exactly z. Z is u divided by sigma. It's a standard normal now. So now that I've reached this point, there's nothing else to do. Right? So I have x beta plus sigma, and then I have to apply this formula here. So I apply that formula, right? The denominator, so here I want the average of this for this being larger than minus x beta sigma, which means the numerator will be this density in minus x beta sigma divided 1 minus CDF in minus x beta sigma, okay? Which is what is written here. Now, to go from here to here, as usual, the normal distribution is nice because it's symmetric. The standard normal is symmetric around 0. So this is my distribution. The density in minus x beta sigma. 0 minus x beta sigma plus x beta sigma. So the density in this point is the same of the density in the other symmetric side. It's exactly the same. So this one minus is the same of this one plus. They're exactly the same. Now, the denominator is something that we have seen when we derive probit. This is the probability. This is the probability that you are to the left of this point, the second point here. You are here. 1 minus this, it's the probability that you are on the right side. Now, this is everything apart from the tail, but because this is symmetric with this one, this probability is the same as everything to the left of this point, which is the positive one. So 1 minus CDF minus something, it's CDF in plus something. Again, coming from the fact that this is symmetric around 0. And so this property we don't have to remember, we just draw this and automatically you're going to see that. So we reached our result. And notice that in this, there is no more error term. So there's no more u. U has disappeared through the fact that I have assumed that the error term is normally distributed. Okay? We assume the distribution of the error term. What we are left is that the average of my variable for values not being censored, now I know it's equal to x beta plus a correction factor. And I know that I need a correction factor. So I know that I need to push x beta to the right, because I know that every time I censor, or I select, so I have the distribution. If this is my average, and I want to move things to the right, so I know that my average will move to the right. That's why I need this correction. This correction turns out that it's just a ratio between density and cumulative distribution function. And it has a name. Okay? This is called the inverse Wills ratio. Okay? It appears in many applications, and it's always the ratio between the density of a standard normal and the cumulative distribution function of a standard normal. So this average here, it's not the OLS. It's the OLS plus this correction factor. So the idea behind this now that we are reaching this point is that if I am, so the first part of my model is telling me what is the probability of being in the OLS side, to be estimated with the probit. Now, what we know is that if we are in that side, then my average, it's a spatial average, which is going to be the original average, x beta, plus this correction factor, which is well known, it's well studied, And that correction factor is going to tell me whether I have to push, whether my mean is going to be pushed a lot or it will be pushed a little. That's telling me, is modeling by how much, when I introduce censoring, how much my average is going to move away from the mean. That's the intuition behind this. Now, the inverse means ratio has this shape. If it's going to minus infinity, it goes to plus infinity. If it's going to plus infinity, it's going towards 0. So when that is very large, there is no correction. So x eta will be very close sorry, the average will be very close to x eta. If there is a lot of correction, then I will have to push it very far away. Okay? I will be pushing it very far away. Notice that everything here comes from here. Right? So from the assumption that the error term is normally distributed. Okay? So without that assumption, we cannot write here, we cannot write this, and we cannot reach this point. So everything comes from two very simple assumptions. Right? So if you remember, we derive all this stuff, but the 2-bit model is extremely simple. It's an OLS or a 0 applied to a fact that the OLS has a normal error. That's nothing complicated, right? So it's very much what we've seen when we applied maximum likelihood to OLS with the addition that I have a problem of observability. That's here. Now, here things becomes a little bit more math, so don't spend time looking at it. This is what we derived. Right? So the first part we said was canceling out. So this is the average of the variable we cannot observe. It's the average of y conditional on x in the non-censored case, something that I do not observe. This part is 0, and this one we have just derived. We know what is this probability. We know what is this average. Turns out that this is how it simplifies. Notice that in this, I know everything. I know the functions of the standard normal, so CDF. I know the density. I have data, but I have a lot of parameters. Right? So I have beta, I have sigma. So what is missing in order to apply maximum likelihood now? So notice that we derive this because now, only now I can compute this. Because that derivative is going to be the derivative of all this with respect to xj. But I cannot compute the derivative because I don't know beta, I don't know sigma, I don't know. So here it's not telling me how do I estimate that. What is step 1 for maximum likelihood? What did we say? What do you do when you apply maximum likelihood? What do you need? Step 1? The distribution. I need to write down what is the distribution that is giving me a data structure that is very specific. A data structure that is not full continuous, but at some point it's a discrete, it's a fixed point, and in the other side is a norm. Okay, so just to get the intuition, this is the density for the 0 values. This is the probability of being 0, right? And if you are positive, you are in an OLS distribution. So no need, you just need to get the intuition. So our density will be very similar to we'll have 2 elements. When you're 0, you follow this function here, that is the probability of being 0. When you're positive, this is an OLS. Right? So it's an OLS with a normal error term. Now you can see that now this in a TOBIT is telling me where my data is coming from. If I observe 0, it comes from this. If I observe positive, it comes from a normal distribution. So I have everything I need, which means I apply maximum likelihood. So log likelihood, I take the log of this, I compute optimality condition, and I derive my results. Okay, so now you derive your results. And this is an example of TOBIT versus OLS. So first forget about the lines, but look at the data. If you just plot points, if you just plot scatter points, say this is the case with one y and one x, so studying the relationship between y and x. If you plot points, you should see immediately that this is a censored case. Right? Because notice that all these points are distributed here, but as soon as you go negative, everything is pushed at 0. Right? And graphically, that's how it's going to look like. So some dispersion of points, but when you go at 0, everything is pushed here. Right? It can be the other way around, but that's the structure that you would observe. So in one point, you have a lot of fixed points, and around all the points, you have a lot of variation. Now, the main difference between TOBIT and OLS, and notice that TOBIT here is computing as a derivative of y by x. So this big formula we derived here, and the TOBIT is given by this. So if I take a derivative of that, I'm gonna get the slope of that function. Right, the OLS is just given by the standard conditions. So if I open this data set and I run the OLS, what is the problem? The OLS will consider the zeros as if those are actual zeros, which means that the more zero I'm going to have going here, my line will just do what the OLS is doing. Right? So minimize the square of residuals, which means it's going to look at the line that is making, yeah, exactly. So it will be becoming flatter and flatter because I'm taking all these slots here, and then you have a lot of points here. So I have many points here and many points here. So I will just connect each point of squares around those points. So the OLS will tell me that the slope here is negative, but relatively flat. But if I look at TOBIT, right? TOBIT model is instead doing something else. It's saying our model is telling us that these points here are not zeros. What is TOBIT doing? It's doing this. What is it going to do? Some push up, some push down. Right? So these are going to be here because for sure down, which means that these are going to be pushed down. Because if it's up, they're here. So this one will be modeled as if they are not here, but they might be down here, and then they're all pushed up here. So that's what the TOBIT is doing. But we don't assume that this is here or here. So what we are doing, we are modeling the idea, right? So the concept that these are not here, but they are down there, and then optimally getting parameters that is telling us what is the optimal model that predicts this given some error term that push me to one side and the other, and some parameters that I choose. So that's what the TOBIT is doing. So notice that if you take the derivative of that is given by the TOBIT model, it's going to assume that these points are not here, but they're going to be pushed down there with some randomness, okay? Which means that this loop is going to be taking this shape. Now, I don't know Right? So the OLS is clearly wrong here if these are non-zeros, because this is estimating an average, right? It's estimating this. But I know that the expected value of y conditional on x is different than the expected value of censored conditional on x. The two have different average because I know that the one that is censored, the average is pushed to the right because I have censoring at 0. Now the two bits, it's adjusting for that, but obviously it comes with the problem that I have to model how my data is extracted. It doesn't mean that that is the real slope. That means that if I model my data the way I modeled, so with this type of error term, then I'm going to get something like that. And remember that it's very important to assume that there is some symmetry in the error term, because this is pretty much saying that this line, which is here, our model is going to predict some on one side and some on the other side, but there's going to be equally distributed. The probability of being one side or the other side is the same. Okay, so let's see a real example. We've seen this quick example on labor supply yesterday. Now we can extend it. It's exactly the same example. It's a labor supply survey. But now I have, this is what we estimated yesterday. But now I have this variable, number of hours. So this variable is going to have 753, 740 of observation, 740 hours average, 871 standard deviation. But this is important. 0 and 4,900. Now this is not always the case, right? Because some data sets might ask you, do you work? Yes, no, right? So if I say no, 0. It's gonna be, no, so let's say that this is one, right? So you ask work and hours.
Hours worked per month.
I don't know if it's per month or per year.
Per year, I guess.
Yeah. Maybe this is a mistake.
Or you wanna
Yeah,
work
740.
4,000 hours.
Yes, we don't have enough hours. So some questioners might ask you, do you work? Right? So it might be if you are ID 1, you work, you say yes, I work. How many hours? If it's 1, how many hours you work? You say 740. And some softwares will say, well, some surveys, they will say, do you work? If you say no, then they skip this question. Right? So this will be 0. So this is important to think about what you do. That's why we start by saying, first thing you have to ask yourself is, what is my population of interest? Because if I do this, right, that means that this variable here, it will be only positive. And it will always be positive, which means that I don't have censoring anymore. So if I just look at this variable, which has many missings, okay, so say that 3 doesn't work, 0, 4 work, 600, 5 work, 500. Right? So you see that if you just use this variable here, the software is going to drop the ones that are missing because they don't contain information. So if I run an OLS on this, I am implicitly selecting as population of interest those who are working, because the rest is not there. But what we are interested here is to estimate effects on the whole population, the people that have been interviewed. Population. So sometimes, if that is your issue, then you will have to say that if you don't work, the value is not missing, but you work 0 hours. That's obviously it's going to change my population of interest. Instead of dropping the zeros, it's going to keep everything. So now, this value, minimum value, is 0. But if we were in the previous case, then this minimum here is going to be positive. So that's why you should always start with summarizing or trying to see what's the average of that. of that file. Okay, so here we start regressing our data in an OLS on the full sample. So the full sample means we are including those that work, those that do not work. So we got all these parameters. We can focus again on education. So education in the OLS is telling us that if I increase education by 1, I'm going to work 28 hours more. That's an increase of 28.8 hours more. Is it correct? Is that correct? If we assume that variable is censored, then it's wrong. Because we are estimating, we are doing this mistake here. So the zeros are assumed to be zeros, not to be censored, to be negative. Because we don't ask, would you work negative hours? So keep in mind that's 28.7. So these are TOBIT estimates. And so we said that in the TOBIT, we have to estimate parameters betas, but also the sigma. Right? So the OLS is not telling me anything about the error term. Right? You see here. Do you see something about the error term? No. Right? There's nothing about the variance of the error term here. There's nothing to write about it. If you look at TOBIT, notice that most software you have to tell your software what is the censoring point. This is telling us there is left censoring at 0. Okay? What L stands for left. The bottom of the code is just telling us what we already see from the descriptive statistics. So I know that we have 325 left censored observations that have smaller or equal to 0 hours. I have 428 which are uncensored, and I didn't specify the right censoring point, so I have 0 observations which are right censored. So at least in Stata, that's similar to other softwares, if I don't specify anything, the upper bound is assumed to be plus infinity, which is what we are assuming. Now, second thing you realize is that now you have this parameter, sigma. Sigma is the standard deviation of the error term. We assume that the error term is distributed normal sigma squared, so we have to estimate that. And so our model will not only recover these ones, but will also recover those ones. Then, how do I interpret these parameters? Now, these here come as a trick, right? Because I'm interested in the derivative of this with respect to value. But my model is giving me sigma and betas. So like the probit or logit. So betas and sigma are not telling me anything, right? Because you see what is the problem of interpretation there. The derivative is very complicated. It turns out that at least Stata, what it's doing, is already reporting this on screen. So that's why it's important to read what the software is printing, because you should know that this, you should know the model behind these softwares here, and you should know what is printing. So remember commands we've seen yesterday, they were printing on screen the betas. The TOBIT is already printing out the derivatives. These are already the derivatives with respect to those data. So you see here that now this slope becomes steeper. And so it was 20, how much? Here, 29, it becomes 80. And the difference is what graphical. We're going to see another example now. But this is, again, this is telling us that if we want to make informed decision, this is answering our question. If I increase education by 1, and I take into account that data are censored, then my effect on education is larger. So why is larger? Why do you think it's larger? Same as before, right? Because some points, instead of being censored, are going to be taken down. So flatter, by flatter, as you what here is positive, not negative, it's going to become steeper because some of the points were flat at 0 and was flattening my line. Exactly. Okay, so as I was saying, this is what we are interested in Tobit. Tobit wants to replicate OLS with that correction. So that's why some software will print those immediately. But as we have seen, Tobit has a lot of potential derivatives that we might be interested in. And so if you go back here, look at how much, even if you forget about this, look at how much parameters of interest we could have. So when I say I change X, I change education, I can answer many questions. First, how much the average of hours worked change? This is what we just asked. But not only, I can ask how much the probability of working change when X change. And I can also ask how much the average numbers of works for those that work change when X change. And because I know everything here, so I know this one, I know this one, and I know the product of the two, that means that I can potentially answer all these questions within that model. So in this example we can see that. And so this is what you just seen. This is the effects of, this is the derivative of the average of y with respect to x. And this is 80.6. Now, most softwares allows you to compute all the derivatives that you want, so I can derive this. It's the effect on number of hours worked for those that work. So expected value of y condition on x for y that is positive with respect to x. And this is equal to 47.5. But most softwares allows you to write whatever you want. You can say, you see that this is telling us the way, this is just a command in data, but there are corresponding in other softwares. This says, I want the partial effects, average marginal effects of dy divided by x for values that are from 0 to plus infinity. And that's what we're saying. So it means that I want the derivative of y, condition on x, for y be larger than 0. Now, behind the intuition, if everything is clear, why this is larger than this? Why this is larger than this? What do you learn about the effect of education on number of hours worked?
It's much more for the people that it's much less for the people that actually work.
Okay, so why? This includes these ones
And it's
and the other ones.
Mhm.
So So why this is larger than this one?
Because the other maybe has a much bigger effect that y equals 0, or less than 0, and when you average them.
Doesn't mean that it's bigger. It means here it's hard to define whether it's bigger, but this is telling you that if I increase my education and I am working, I will increase the number of hours worked. And this is telling me if I increase education, then the number of hours worked among everyone will increase by more than this. That means that education has two levels effect. The first one, if you work, you're going to work more, but at the same time, it's going to drive people from not working into work, from 0 to a positive number. That means that's why the overall effect, this includes extensive and intensive margin. This focuses primarily on the intensive margin. So this means I'm going to be working more. I work already, but I'm going to be working more. This is telling me I'm not working, I will start working. And obviously, if I don't work at 0, if I start working, I'm going to have a positive number, which means that the overall effect is picking up these two dimensions, intensive and extensive margin, which are at the core of the design of these models, which assumes corner solutions. Right? So solution where I have a mass at 0. Let me see. Visualizing this stuff. Obviously, in the previous case, it's hard to visualize because I have many variables. Right? I cannot visualize in the example we've seen before because in this example here, because to visualize this, I need two variables, right? So an outcome variable and one x. In these regressions here, I have many variables, right? So it's harder to visualize what is the correction of my estimate. So we can try, just as an example, to say, what if we try to estimate the effect of income, daily income, on number of hours, assuming left sense. So I dropped this part from the previous figure for simplicity, but this, you see, that log likelihood is not, doesn't provide a closed form solution. It's gonna be looking for minimum or minimum or maximum times our splitting, but it's gonna be looking at it numerically. So that doesn't mean that this model has a closed form solution. It has another formula that solves everything, because it might be too complex. The problem is the same as before, right? So 753 observations, some are uncensored, some are zeros, some none are right size. We got that coefficient is minus 17.58 negative. If you run that, imagine that you run two mistakes. Right? So you make a naive estimate and you do the following thing. So first thing, you say, well, let's estimate OLS. I take the same sample, I just run OLS. OLS is a closed form solution, right? You see there's no integration here, it just spits out my formula, I guess -9. Then you say, well, maybe I know that a lot of people are zeros, I know that zeros are creating problems, and then I say, why not estimate OLS only for those that work? These that work. I guess -5.97. All right, so if we visualize this stuff, we're gonna see the following. Graphically, it looks pretty much what you've seen before. Right? So there's not, even independently from looking at hours of work. Right? So if I cover this and you don't know what these variables are, if you see something like this, it's already indication that points are shifted up at 0. Or there is some mass at 0. You see that because you see you have a lot of points here. They almost cover each other. And you have a lot of points here, but you see that they are dispersed and not many points here. So the fact that you have a lot of points here, it's indication that these points have been compressed from one side at least around 0. Now this is the OLS, this is the OLS. First is full sample, this is positive values, this is Tobit. So how do we interpret that? So first of all, you see they all have different slopes.
Yeah.
Right? The orange line, almost flat. Green line, steeper. Tobit, always steeper. Is this wrong or correct? So there is something wrong and something correct. It really depends on our assumption. What is the orange line telling us? So positive values. The orange line is OLS on those that are positive, among those that work. So this is not implicitly wrong. So this is a derivative of partner's income or number of hours worked in the population of interest that we choose, which is those that work. Now, those that work are very different from those that do not work, which means that this is a very specific estimate that we actually see. Then, going on the full samples, we encounter exactly the same problem. So the OLS will be particularly giving a lot of weight to outliers. Right? So if I have outliers that are very far away down, and they're compressed here, I'm going to have more here. So this line is going to shift up and up to pick these points here. But it's already different because you see the change with relative to the orange went down and it becomes a little bit steeper. But we are obviously not making a mistake. We are making a precise assumption. These zeros are zeros. They mean zero. And the issue that having so many zeros at that mass creates a problem for OLS because it's really much dependent on how many points they're going to here.
So the reason why the orange line is less steep is that since it doesn't have to count for the difference between the zeros and the actual mean, the difference is smaller in overall.
This is flat for this reason, is that if you just take the positive numbers, you have these points here.
Yeah.
Now, this point here is noise. So that means that this line here is mostly estimated in this part here.
Okay.
That's how it is estimated. So you're going to have points up, points down, which means this is going to be flat. Then I do have some points here, but very few.
Yeah, so
but because the OLS we said it's going to smoothing globally this data, you can estimate it mostly from these points, and then the rest is going to be pretty much extrapolated. Right? Because this relationship, because this is linear, it means that the relationship that is from going from this point to this point is the same of going from this point to this point. If I was making it non-linear, maybe this would have looked something that that is going to be looking like this. Maybe, I don't know. It's hard to say in this setting, but we assume it's linear. So it's going to be taking much of this relationship in these parts and then extrapolating it. Now, the big difference between these two, they use the same sample, and why Tobit is important. Notice that here you don't have much of distinction because I'm using only one variable. But what is the Tobit doing is going to be taking these points here and assuming that these are not zeros, but they're going to be negative, somewhere negative. We don't assume where, but they're going to be somewhere negative. And if you assume that these are negative, obviously, if the OLS is negative, Tobit will be steeper negative. That can only be steeper negative because the difference between this one and this one is not big, right? This one and this one are both OLS, which one difference that is the Tobit is OLS, assuming that some points are censored at zero. Now, three other points, and we can see it here. Very similar to the to the problems, all the nonlinear model, right, all the models that suffer from the assumption we have seen, always suffer from the same three problems, which I have written here. Omitted heterogeneity independent of the covariance. So if I forget an important variable, my estimate will be biased towards 0, okay? Attenuation bias. Models that are nonlinear requires that we put in important predictors of the outcome there. I cannot forget about that. And the reason being, as usual, is that those derivatives contains all x's. So if I forget one important x, then my derivative is not going to be correct. Second point, well, second and third points, they relate with the assumption about u, right? 0, sigma squared. If my error term is not homoscedastic, like here, then everything I derive is wrong. What does it mean in practice, in this case? So our basic Tobit model assumes that once you are going down here, I will always have an x beta, but I will always be from x beta. Let's remember that it's here. X beta, then I'm going to have a u on top, and I'm going to have the sensory point here. Right, so if I'm going down here, I'm assuming that for every x beta, this error is always the same. But it can be that if I'm here, if I'm here very close, maybe my error term is much more concentrated. It's much closer. Which means that for these people here, being negative or positive, it's really dependent on x beta, not much on the error term. While for these people, being positive or negative depends on x beta, but a lot on heterogeneity. So I have a lot of people that are here, but a lot of people there, and a lot of people here. So if I have this type of structure in the data, then what we have been doing is wrong. Because we have been assuming that this error for these people and this error for these people have exactly the same distribution. That's very important. Everything that relies on distributional assumption is not going to allow me to recover the correct parameters because of the mistake in the way we formulate the problem. And final issue.
Perfect.
Yes.
So when we graph the distribution of the error of the d equals 0 and d equals 1, they must have the same distribution. Otherwise, we're doing something wrong.
We are not blocking, we are assuming. And so the Tobit is here.
And how do we prove that?
Tobit is assuming this. It's assuming that we have an OLS, we observe only the OLS when it's positive, and we assume that the error is 0 sigma squared. And your question is, when do we know it's correct? We don't. Right? We are playing a trade-off here. Do as we always said. Do you want something simple, easy to interpret, OLS? This model here is telling you the OLS is going to give you this problem that if I have a lot of sensory, it's going to flatten up a lot my estimate. It's going to make my estimate close to 0. So you have to take a trade-off. I want this model that is very flexible. It's more flexible. I'm going to feed the data, but I have no clue, right? Because my data is just this one.
And there's no statistical way to approximate maybe.
You can play around with these, changing these, but imagine how many functions you can find to say this variance here is a function of 1x, maybe it's function of all x's, maybe it's a very special function. So you don't know what's the underlying distribution. So the way that we deal with this, we make models that are more flexible, but we try to keep these assumptions in the most simplest way. So that's why if you go on statistical software and you press topics, you're not going to have a way to model this. You're going to get this because it's the simplest one, and it makes some assumptions that are pretty acceptable. But if my underlying variable was determined by a different error term, then this model will only recover something that is close to that, but it's not exactly the same. That's the cost we are facing. Then some people might go very advanced in this. Maybe that's your job to do this stuff. You can model this and try to see what model performs better at predicting your output variable, and then you can try all possible models. So there's no way to say what is correct.
But before, when you were comparing the coefficients, what was the reason the Talbot estimate had 80 and the other one 28? What was the reason you mentioned? Why the coefficient of the Talbot was 80 compared to the education? What was the reason between having a high one on slide 29? So that one's
That's 128.
yeah.
This one is 80.
So you were explaining the reason.
The reason why they're different is exactly this one. Right? So it's the difference between this one and this one. Now, in the table, they're positive, but it's exactly the same one, right? So the OLS will give you a flatter because instead of going down steep, I'm taking points towards zero. If it's positive, it's exactly the same. Right? So if it was like this, I have many points at zero, so the OLS will rotate down and be close. That's why the two are always, the OLS will always be closer to zero, because I assume that zeros are actual zeros. COVID assumes that zeros are somewhere negative, and I model them with some assumptions that allows me to make some more informed decisions on that relationship. OLS will always be smaller, yes. Actually, there is a slide I have not, if I have it here. Yes. This is a result that sometimes is useful, sometimes it's not. So the Tobit, the interpretation of the Tobit derivative is always this one. It's beta j OLS multiplied by a probability. Now, this probability, it's always in between 0 and 1. So when this probability in between 0 and 1, it means that the OLS will always, so this is the Tobit. The OLS will always take the Tobit multiplied by the probability and shrinking it towards 0. And so that means that all the time, what the OLS is recovering, it's going to be smaller than the Tobit. Now this is another interpretation, it's written here. This is the probability of being non-censored. When the probability of being not censored is very close to 0, right? So when I don't have censoring points, that Tobit is the same as the OLS. That's straightforward because the Tobit is a mix of probit and OLS. So if the probability of being a probit is very close to 0, then Tobit is estimating an OLS. If I have a lot of censoring points, so the share of censored is very large, then the two are going to be very different, where the OLS will be very close to 0, and the Tobit will make a very large adjustment. Okay, so that's the intuition behind the interpretation of these variables. Now, we are not going to cover this, and we end this topic. If you know how to derive this, we derive this for 0. Right? So that's what we have been seeing today. So you know how to do it. It means that you can, or you should know, not so complicated. You can also estimate this. Right censored, which can be 0, can be points. So please call it A, call it B. You can, if you know how to estimate this and estimate this, you can also estimate them together. Things are becoming more complicated because if you have 2 censored points, I'm going to have 2 profits and OLS in between. So imagine that this is censored here. So this part goes away, and here you're going to have a mass of B. Then I will have to estimate the probability of being to the left, probability of being to the right, and OLS in the middle. You're going to have 3 elements. And if you know to do this, then you can do this. And this is pretty much having many censored points, which is called interval coded data. You will never use this, but the day you're going to wake up and say, well, today I really want to derive an estimator for a data that is interval censored with some censoring on one side, some censoring on the other, then you know you need some math, some derivatives, some maximum likelihood, and all right, so we didn't have time to look at selection models. If you're interested, there are slides up there. The difference between this and the topic on selection models is to focus, instead of censoring, to focusing on truncated data sets. Okay, so places where I don't know what is the variable. Typical example is I want to know about wage, relationship between education and wage, but I know that wage is not 0 for those that do not work. Okay? So the wage for those that do not work is uncertain. Okay? We don't know what it is. So in those cases, we are in more of a censored, rather than censored, we're going to be in a truncated, but we're going to be in an even more complicated case because the fact that I am in the truncated parts or in the non-truncated parts depends on a choice. Okay, so we call that self-selection, and selection models like Ekman selection model is one that is applied. If you're interested, you have the slides. These are models where we're going to be modeling why we make certain decisions, why I decide not to work, and they are models that will try to recover a relationship between variables, let's say education and wage, by making certain adjustments such that we know what is the relationship between wage and education and wage, also for those that do not work. Okay, so we call those models selection models. I think today you had enough hours, so you can go for a drink or go to sleep.
More like the second.
Hasta las 6 horas son 2 horas de TDAH. Sí, pero porque no tengo el celular, tengo el celular, yo te estudio